everyone, including Trevor.
Thank you.
Chase. Hello.
You guys are so weird.
What is going on? This is the way to start a video. You should know that.
Here we go. All right. I need to make sure that you have your braids with you today. We good? Shaw? Yes? To pay attention and think. Here we go. So one can gain information about the rate of a reaction by seeing how the rate changes with changes in concentration. All right. So our goals, I wrote these years ago, so we'll see what these actually say. Our goals today are to use data tables to determine reaction rate laws, which you've never heard of what the rate law is. But the rate law is just going to be something that says rate equals concentration of A raised to some number, concentration of B raised to some number, and that will be, oh, sorry, there's a constant right here. Now, this is the first time I think that we've introduced this type of constant, and we're going to have a lot of them from now on. And they're, in my opinion, incorrectly named constants because they're different for every reaction at every single temperature. So they're never a constant, but they call it the rate constant. Anyway, we're going to use data tables to figure this process out, and it's kind of fun. Like I really do think this is sort of fun. All right, then we're going to use rate laws to solve for the constant, or K, and then we use K and rate laws to solve for unknown concentrations and at different times. Those are our goals today. They're actually not hard. If you're above average intelligence, which most of you should be, this won't be that bad. So here we go. So in this, and we're going to teach you a couple ways to find rate laws, and they're going to look very similar, but they're very different ways. So make sure you understand. If you are given a data table that lists various experiment trials and then initial concentrations and observed rates, then you have to follow what we're doing today. You're going to learn other ways to do this where you'll be given a data table, but it's a different style of data table, and you need to do math completely different. All right? So this is the first thing. So here we go. You will notice if we compare experiments 1 and 2, when the concentration of this is doubled, all right, this is held the same, our rate doubles. That's what you would expect. Like, you're like, oh, that makes sense. If I double it, it doubles. It doesn't always do that, but if it does, that's good. What we're trying to do, by the way, is we're solving for this exponent. All right. That's not what I want to happen. How do I explain this better? Anyway, what we're going to do, we'll find this in a second. We're finding out if I do something to this, yeah, that was supposed to be a 2, I'm sorry. If I do something to this and it's raised to some exponent, and then it gives me an answer, I can find that exponent. So here we go. If I take whatever my concentration is and I double it, and I end up with my rate being doubled, then what must this exponent have been? What number can you raise something to and it stays the same number? A 1. All right? So what we would say about this reaction is if you tripled it, what do you think would happen to the rate? Times 3. We'll call this a first order reaction, or we will say that this exponent is raised to the first power. All right? We'll get to this again in a second. But sometimes we put a 2 in here, and our rate, I just jumped ahead of myself, increases 4 times. Well, what exponent can turn a 2 into a 4? A 2. So we would say this is a second order reaction. Not very often, but once in a while, we put a 2 in here and our rate becomes 8x. What exponent makes a 2 and 8? 3. All right? So what we're going to do, we're going to use data tables like this to see what happens to the rate when I make a change so we can find that exponent. That exponent will be called the order of the reaction. Are we all right with that so far? Okay, so based on just experiments 1 and 2, where's the tool I want? I was able to determine that the concentration of NH4, and that's a plus, is first order. If I double it, the rate doubles. All right, now I want to figure out about the other half of this, which is NO2 minus. So I come over here and I find when these are held constant, and I see what happens over here. So NH4 is held constant, so I come over here and this is doubled. Are we all right with that? All right, so this is 2x. What is my rate here? It's hard to see, but it is also 2x. Are you okay with that? So we would say that NO2 minus is also first order. And we would then also be able to say that the overall order of this reaction is a second order reaction. Because if I doubled both would double, so it'd be 4 times faster. Are you okay with that sort of basic logic? Go ahead. You'll learn that in a minute. The order is going to determine, it's not in a minute, it's actually in a while. It determines how many independent things have to collide at the same time for a reaction to happen. All right, yeah.
He said first order, so I was thinking it's going to be second order. It'll probably be a new order.
That's pretty deep. Good idea. Okay, glad we got that. Okay, now look. Rate laws. Rate laws are written in the following format. We would say that the rate of this reaction is equal to K, which I don't know, but it's a constant, times the concentration of NH4 plus raised to the first power times the concentration of NO2 minus raised to the first power. Bruh. What?
I'm just like, you just walked through so fast.
I was only ready with that because my kids bruh me all the time. And that is one of the fastest ways for them to end up in their room. There's a faster way. Do you know how? Nope. Nope. No. No. It's close. You're a good listener. No, when they bruh my wife. And it's like, all right, should I? Never mind. I won't say that because this is being recorded. But it's rude. All right, now, here's the magic of this equation. It's sort of pointless right now, but it sort of isn't. If you will look, we have 8 rows of data that give us concentration, give us rate. So we can use any of those 8 to do what? To solve for K. And once we have K, then we could make whatever concentration we want, and we could figure out what the rate would be. You okay with that? Like, it's sort of genius and sort of not hard in the like hierarchy of hard things that we do in this class. This is not that bad. So here we go. Hopefully you have that written in your notes. let's find out what K is equal to. Can you see this table good enough, or do I need to zoom in on it? All right, solve for K. All right. If we rearrange this, you should get very comfortable with doing this because you'll do it more than once on the test. You'll do it a lot in your homework. It's not bad. We will rearrange and we'll say that K is equal to rate over NH4 plus to the first, which math calculator-wise doesn't really matter, NO2 minus to the first, and that will be what our K is equal to, right? So I just took the top row, the rate, anyone write it down? And I'm going to divide that by 0.01, is that what it was? Yeah. Times 0.2, and I don't know, what do you end up with? 2.7 times 10 to the what? So that is our K value. That's not that bad, right? All right. The next part, and there'll be other problems, so I don't know if we'll continue this one. The next part would be like experiment 9. I would say you have 0.25 x and 58.6 times 10 to the negative 7th. Then you could solve for your concentration of that one just with algebra. Are we okay with that? That would be the next step. Now, I've never done this before, but I might as well do it now. I usually don't teach the units for K until the end. The unit of K can be an absolute nightmare. This one will not be that bad. So these are molarity, molarity, and molarity seconds. Are you okay with that? So this, make sure we're okay. So when we do the unit, I'm going to erase all this because we already have that part. And I'm just going to put the units. The unit of rate is molarity per second. Are we okay with that? If you'll do this just super detailed, you'll be fine. It's molarities per second. And then the concentration down here was measured in what? This was just molarity, and it's not squared or anything, so it's just molarity. And then what's this one? It's also molarity. Are you okay with that? All right, and then you cancel out anything that repeats on top and bottom. So I can eliminate an M from the top and the bottom, right? So I cross the M out, and kids are very uncomfortable with nothing in the denominator or the numerator. It's a 1 over, or you'll see this listed as S molarity to the negative 1. That dot won't be there. I don't know why I put it. Actually, they always put molarity first. Molarity seconds to the negative 1. That would be the unit. You okay with that? Okay. They get more complicated when we use different units and when we're squaring and tripling and stuff like that. But if you just will put one fraction out and be very good at keeping things in order, they're fine. They just take some time. Okay. That's pretty much using data table to determine the reaction rate law. Use the rate laws to solve for the constant. And use K rates to solve for an unknown concentration. That's our goals today. So that's the same table. Whew. My left eye is wigging. Technically my eyelid. All right. Here's some qualitative information about the rate law. Let me shrink this down. Oh. Oh, I know what happened. It probably had some weird symbols, so I just cut and pasted good ones over. I have no idea what's going on. Good enough, right there. All right, so rate law shows the relationship between the reaction rate and the concentration of reactants. Sorry. The exponents tell the order of the reaction with respect to each reactant. And we've already said this. We realized it was first order with respect to both of them. There are reactions that go back and forth for a while, not forever. They eventually reach what we're going to call equilibrium, but they keep going. If on a sub day, have I showed you the chemical curiosities videos? Probably not, because I don't usually for AP. But there's a video called Chemical Curiosities, and the guy does demos throughout the whole time. And while he's doing it, the very first one he did, might be the second one, it keeps changing color if you watch. And it's doing that, but eventually those do end because they reach this state of equilibrium, which is what chapter 15, 16, and 17 are all about. All right. The overall reaction order can be found by adding the exponents of the reactants in the rate law. This particular reaction we've been studying is second order overall. All right, so here's a practice problem. This is from an AP test in 1987, the B form. The equation for the reaction between mercuric chloride and oxalate ion in hot, yada, yada, yada. Who cares? Look at that table. You have experiments 1, 2, and 3. It says, according to the data shown, what is the rate law of the reaction above? On the basis of the rate law, calculate the rate constant and specify the units. I'll give you 5 minutes. See if you can execute that. Do you need the table bigger, or is it good enough? Okay. Give that a shot. It may be as easy as we just did. It looks like it's not already. Through this one together. So it says, what is the rate law for the reaction above? This one is a little bit harder, but not that bad. First off, in this reaction, Hg is held constant, and we change this. So when we go from here to here, we double, right? What happened to the rate? It quadruples. So how does a 2 become a 4? If it's squared. So that means that C2O4 2 minus will be squared in my rate law. Who had that piece right? All right. Then I come to the next one. And here, this one's held constant, and this is doubled as I go up, correct? And that's legal. They can do that going up. It's annoying, but it's allowed. So from here to here is roughly doubled, right? Sometimes they're not exactly, but they're close enough. So a 2 stays a 2 if we raise it to the first, correct? So what is the rate law? All you have to do is this. You write rate equals K, and then you're good. You have answered that question completely. Don't forget the rate law, though, like to write it out. On the basis of the rate law determined in Part A, calculate the specific rate constant, specify the units. I don't know why C is not on here. C, by the way, is to find the question mark, so we'll do that also. All right, so the rate law, the rate constant, K will be equal to rate divided by C2042 minus squared and HGCL2 to the first. And you can just pick any row you want. I always choose the top one, so I don't look somewhere else. It's like singing a song. I'm really good at singing the parts on the first and the last verse. I'm really bad at singing parts in the middle too. I can't read the middle and the lines. And anyway, so pick one of these. It's easy. Sorry, singers. I respect you. Okay, did I keep the numbers in the right spot? Am I squaring the right one?
Yeah.
That's the most common screw up on this. Is you, whoops, oh crap, hold on. There we go. Sure, that's enjoyable on the video. Is when we just put the wrong one in the wrong place. When you did this and you solved for K, do we have more than one person that thinks the same value? 0.015? Who agrees with that? Okay. Okay, so that would be the answer so far. Specify the units. Oh, barf. So here we go. I'm going to erase all this again, just for ease of writing out the unit. So it told me the rate was moles per liter, and I'm going to write it out exactly how it put it. It was a mole on top, a liter on the bottom, and a minute on the bottom. That's so far just the units from the rate. Then I have, they're capital M's, so I have molarity squared, right? And molarity, or molarity cubed. You okay with that? All right. What is a mole per liter right here? Okay, so everyone look at me. If you have a mole over liter, you can just call that a capital M on top. So really, that is gone. One of those is gone. And you're left with your rate constant unit being minutes to the -1, molarity to the -2. You okay with that? It's weird. It's doable. You just got to make sure you're good at counting. Okay, then I can't remember why, or I don't know why. C got deleted right here. C just says to solve for this value. Will you do that now? And by the way, real quick, the unit of K isn't a real thing that exists. It's a unit that makes all the math work out so the other answers have the right units. Right. It's not a thing. It's just a thing that makes all the numbers talk to each other. So don't like try in your head thinking, what is a 1 over molarity minute? I don't know. Okay, solve for C real quick. What was your answer?
0.514.
Do we have people that agree with that? Raise your hands. 0.514. Okay, we'll work through it then since half of you don't have that value.
Wait, hang on,
I'm just going to change those because I'm lazy, don't want to write them. Are we okay with that? So y was raised to the first, wasn't it? And z was raised to the second. Good? All right, so when we solve for c, we're solving for that one, correct? Which we take all that over, so it's equal to rate over, we'll get the square root in a second. So K and the concentration of Y goes on the bottom. Are we all right with that? And then that's everything. We got to get rid of the root or the 2. And that will be equal to what we want. Okay, so I'm calling that X. Then just plug it in. We have rate, we have the K, we have Y. And you told me it was 0.015. Is that what you said? I don't know where I got the other answer. Still not good? That's fine. Yeah, it's fine. Okay, are we comfortable with this, on how to do this? It's kind of nice because they are sort of hard problems. They're a high likelihood of being asked, but they're doable. Okay, here's another one. What we're going to do, I have to go to the junior high for their B time, which starts in like 7 minutes. So I'm just going to leave this up on the screen. What's the rate law? Calculate the rate constant. Solve for X. Same thing we just did. If you get done, you can work on homework or just sit quietly. Sound all right?